In our last video, we were looking at the parts of a galvanic cell. So let's talk about what the different parts are of our galvanic cell. We have the half cell. There happen to be two half cells. Just remember, two halves make a whole. The half cell is one part of the galvanic cell in which either oxidation or reduction occurs. So in one half cell, you have oxidation occurring, and in the other half cell, you have reduction occurring. As I mentioned, there are two half cells. Two halves make a whole, two half cells. The second part of the galvanic cell you want to be familiar with is called the salt bridge. This is a porous partition, or it could be a U-tube, a U-shaped tube containing an electrolyte. That's why it's called a salt bridge. It contains an electrolytic solution that connects the two half cells. It sort of completes the circuit. If the salt bridge was not present, the cell would not work. It would not be a completed electrolytic cell. This is what keeps the charge in each compartment from building up. It keeps the charge in each compartment neutral to zero. As I said, it also completes the circuit. The third part of the electrolytic cell is called the electrode. There's two electrodes. This is the surface where the reaction occurs between the electrode face and the solution in the half cell. So it's actually a metal surface usually. It could be a surface like with it could have a metal surface that would have hydrogen gas as the electrode, but this a metal electrode. So one of the electrodes is referred to as the anode and the other is the cathode. As I mentioned, this is usually a metal strip, and this is the place, the thing that carries the electrons from the solution up through the wiring that connects the other half cell. There are two types of electrodes. We have an anode, which is where oxidation occurs. Again, remember, anox. And then you have a cathode where reduction occurs. So I told you to remember red cat. Anox and a red cat. If you pair that up with Leo goes grr, remember Leo means if you lose electrons, you oxidize. And if you gain electrons, you reduce. Here we see two different diagrams of electrochemical cells. Here you see the two half cells separated completely, but they're connected by the salt bridge. Notice the salt bridge is immersed in the solutions, and these are your electrodes. Here we have a zinc and we have a copper electrode. Notice there's a wire that connects the electrodes, and on this one, it's powering a light bulb. If you were to take the salt bridge out, the electrochemical cell would not work. Here we have the porous partition that I mentioned earlier. So there is a partition here that's porous that allows the sulfate ions to permeate through from one side to the other. Notice the electrons are flowing, and they always flow. Electrons always flow, I want to mention, and we'll look at this later in the lesson, from the anode to the cathode. Okay? So I want to take just a few minutes to take a look at a little animation of a galvanic cell.
A useful galvanic cell can be constructed by using zinc and copper. The anode is a zinc bar placed into a zinc sulfate solution. And the cathode is a copper bar placed into a copper 2 sulfate solution. The two solutions are connected by a porous sodium chloride salt bridge that prevents the two solutions from mixing but allows ions to migrate. Attaching a cell shows that electrons flow from zinc to copper. Because zinc is a more active metal than copper, it is more likely to lose electrons. For this reason, the zinc bar is oxidized. producing a zinc ion and 2 electrons per zinc atom. The copper ions in solution gain 2 electrons and are reduced to copper metal. As the reaction continues, excess positive zinc ions build up in the zinc solution. At the same time, the loss of copper ions from the copper sulfate solution creates an excess of negative sulfate ions. Positive sodium ions migrate into the copper sulfate solution from the salt bridge, while negative chloride ions migrate from the salt bridge to the zinc solution and maintain neutrality of the solutions. The reaction stops when the zinc bar or copper ions are depleted. The overall cell reaction can be written like this. A useful galvanic cell can be constructed.
I also want to take a look at another little animation that in this case they have the U-tube U-shaped salt bridge here. So let's look at this animation as well. This is a copper zinc electrochemical cell as well.
Let's zoom into the atomic scale and see how this cell operates. Here at the anode, the site of oxidation, zinc atoms in the metal bar are in contact with the surrounding electrolyte solution. Each atom loses 2 electrons and becomes a zinc ion, which diffuses into the solution. The electrons given up enter the bar and join the flow of electrons up toward the external circuit. They travel through the wire and flow into the cathode, the site of reduction. When a copper 2 ion in the cathode solution makes contact with the copper electrode, it gains 2 electrons and is reduced to a copper atom, which deposits on the bar. Therefore, as the cell runs, the zinc anode becomes lighter and the copper cathode heavier. Now let's close in to see the role of the salt bridge. The non-reactive sodium and nitrate ions of the salt bridge prevent the buildup of charge that would occur as zinc ions enter the anode solution and copper 2 ions leave the cathode solution. Such a charge buildup would halt cell operation. In the anode compartment, nitrate ions leave the salt bridge to balance the gain of positive charge as zinc ions enter the solution. Some zinc ions also enter the salt bridge. In the cathode compartment, sodium ions leave the salt bridge and nitrate ions enter it to balance the loss of positive charge as copper 2 ions leave the solution and are reduced at the cathode.
All right, so let's go back to our PowerPoint and pick up. So in your galvanic cell, the electrons always flow from the anode to the cathode. So in this one, remember I mentioned earlier that it does show the flow of electrons. We always want to label our flow of electrons whenever we're labeling our galvanic cells. Notice here it shows electrons flowing from anode to cathode. Now, if we go back to that table of reduction potentials that I showed you on the earlier slide, and you will get that handout in class. If you notice here, zinc plus 2 electrons yields the zinc atom. So this cell potential is negative 0.76. If you look at where the electrons are, you see the electrons are on the reactant side, so they're being gained. So remember, if you gain electrons, you reduce. This is your reduction half reaction. Here is also a reduction half reaction for the copper ion. Now, you can't have two reductions occurring. Remember, with a galvanic cell, you have one is oxidation and one is reduction. So for your process to be spontaneous, your cell potential has to be positive. Now remember, delta G is what's negative, but the cell